Started on section 6.5, Indirect Proofs and Triangle Inequalities. Our lesson objectives are that mathematicians will be able to write indirect proofs, list sides and angles of a triangle in order by size, and use the triangle inequality theorem to find possible side lengths of triangles. So our essential questions: how are sides related to the angles of a triangle? How are any two sides of a triangle related to the third side? All right, so let's start by getting familiar with some vocabulary. So indirect proof, it's a style of proof in which you temporarily assume that the desired conclusion is false, then reason logically to a contradiction, which proves that the original statement is true. Here are your 3 steps for writing an indirect proof. Step 1, identify the statement you want to prove. Assume temporarily the statement is false by assuming that its opposite is true. Step 2, reason logically until you reach a contradiction. And then your final step, point out that the desired conclusion must be true because the contradiction proves the temporary assumption false. All right, to clarify, an indirect proof or proof by contradiction. Basically, your theorems have been consisting of 2 parts: the hypothesis, which is your given statements, and a conclusion. So far this year, our method of proofs have been direct. In other words, we start by assuming all the hypotheses are true and then produce a sequence of statements, each of which is fully justified by the hypothesis or by postulates, definitions, or other proven theorems. And the final statement should be the conclusion of the theorem, following directly from the others. So for an indirect proof, we're just assuming still that the hypothesis is true, but in addition, we're assuming the conclusion's false. And our goal is to produce a contradiction which causes the assumption to be clear that whenever the hypothesis is true, it is impossible for the conclusion to be false. In other words, whenever the hypotheses are true, the conclusion must also be true, which proves the theorem. So let's see this indirect proof in action. We want to write an indirect proof that in a given triangle, there can be at most one right angle. We're given triangle ABC, we want to prove that triangle ABC can have at most one right angle. So we start by saying that the triangle has more than one right angle. This assumes that angle A and angle B are both right angles, so the opposite of what you're trying to prove. So this leads us to say that if we have both right angles, then measure of angle A equals measure of angle B, which equals 90 degrees. This leads us to thinking about the triangle sum theorem, which states that the sum of angle measures in a triangle implies 180 degrees. So we can say that all 3 angles add up to equal 180. Well, if we substitute the 2 values we already know, which are both 90 degrees, and to figure out that third angle, we would solve this equation to get 0 degrees. This means there's no triangle because you cannot have an angle measure of 0 degrees, which contradicts the given statement. So this is the point where you have your contradiction of the 2 statements which cannot both be true at the same time. So the assumption is that angle A and B are both right angles must be false. Therefore, triangle ABC can have at most one right angle. All right, now let's take a look at relating the sides and the angles of a triangle. So in other words, our angle-side relationships. We can draw an obtuse scalene triangle. We want to find the largest angle and the longest side and mark them in blue. And then find the smallest angle and the shortest side and mark them in red. What do you notice? Well, hopefully you're noticing that the relationships are true, that the longest side and the largest angle are opposite each other. And then for the shortest side and the smallest angle, they're opposite of each other. So in this example, we can see that the relationship can help us decide whether a particular arrangement of side lengths and angle measures in a triangle may be possible. So the relationship between our angles are the largest angle is always opposite of the longest side. This is true for all triangles. And the smallest angle is opposite the shortest side. This is true for all triangles. Next, let's take a look. This leads us to the longer side theorem. It states if one side of a triangle is longer than the other side, then the angle opposite the longer side is larger than the angle opposite the short side. So our implied statement can be shortened down to, in a triangle, angle opposite longer side is larger. So looking at this example, we see that since AB, side AB, length is less than the length of AC, then we can conclude that the measure of angle C is less than the measure of angle B. So shorter side is opposite smaller angle, longer side is opposite larger angle. So we can say that angle C is less than measure of angle B. You can also change that around and say that measure of angle B is greater than measure of angle C. So here's the main idea. Big side goes to the big angle, and the small side goes to the small angle. All right, so we also have the larger angle theorem, which states if one angle of a triangle is larger than another angle, then the side opposite the larger angle is longer than the side opposite the smaller angle. So shorten that to our implied statement, in a triangle, side opposite larger angle is longer. So here we have angles 50 degrees and 30 degrees. So since measure of angle C is less than measure of angle B, then we can conclude that side AB is less than side AC. Main idea, our big angle goes to the big side, the small angle goes to the small side. All right, so let's take a look at a proof of the triangle larger angle theorem, and we'll prove indirectly, so an indirect proof, in other words, by contradiction. So we were given that measure of angle A is greater than the measure of angle C, and we want to prove that side BC is greater than side AB. So our first step, assume temporarily that BC is not greater than AB. So in other words, you do the opposite of what you're trying to prove. That's what you start with, opposite of what you're trying to prove. So then it follows that either BC is less than AB or BC is equal to AB. So if we're proving that it's not greater, it's either going to be less or equal. So our second step, if BC is less than AB, then measure of angle A must be less than measure of angle C by the triangle longer side theorem. If BC is equal to AB, then measure of angle A equals measure of angle C by the base angles theorem that we learned in chapter 5 for an isosceles triangle. Step 3, both conclusions contradict the given statement that measure of angle A is greater than measure of angle C. So the temporary assumption that BC is greater than AB cannot be true. This proves that BC is greater than AB. So a common error to watch out for is be sure to consider all cases when assuming the opposite is true. All right, so let's look at ordering angle measures of a triangle. We're constructing a stage prop that shows a larger triangular mountain. The bottom edge of the mountain is about 32 feet long. The left slope is about 24 feet long. The right slope is 26 feet long. List the angles of triangle JKL in order from smallest to largest. Start by drawing the triangle and labeling all the sides. We can see that the shortest to longest is JK, KL, and JL, which means the angles opposite of the smallest would be L, then J, then K. So by the triangle longer side theorem, the angles from smallest to largest are angle L, angle J, and angle K. All right, so now let's take a look at our sides and putting them in order from shortest to longest. Okay, so take a moment to sketch the picture of triangle DEF with the given angles 51 degrees for angle D and 47 degrees for angle E. First, we need to find that missing angle measure. And we know that by the triangle sum theorem that all three angles in the interior of a triangle will add up to equal 180 degrees. So we can set up our equation, measure of angle D plus measure of angle E plus measure of angle F equals 180 degrees. By substitution, we get 51 plus 47 plus measure of angle F equals 180. So we add those together, subtract from 180, we get measure of angle F equals 82 degrees. So the angles from smallest to largest are angle E, angle D, and angle F. The sides opposite these angles are side DF, segment EF, and segment DE respectively, in other words, in that order. So by the triangle larger angle theorem, the sides from shortest to longest are DF, EF, and DE. All right, now please pause the video and you try these two where you're ordering angles and ordering sides. Try these on your own and then unpause the video to reveal your answers to see if you got them right. All right, take a moment to check your answers. So pause the video and see if you got yours correct for numbers 2 and 3. All right, so this leads us to the triangle inequality theorem. Not every group of 3 segments can be used to form a triangle. Let's take these 3 examples as case in point. Our first image here on the left, I've got segments of length 4, 5, and 2. So I know that if I were to place my longest side first and then connect the next 2 at the end points of the 5 unit length segment, the other 2 would meet and connect to form a triangle. But take this next example, I've got a 5, a 2, and a 2. So if I were to try to connect these 2s, they wouldn't completely connect. They would end up falling down flat on the side with the 5. So these links do not connect to form a triangle. And the same thing is true here. With this example, the 3 and the 2 connect and would fall down and meet together on that third longest side. They would not form a triangle. So this means that lengths of segments must fit a certain relationship. So this does lead us to the triangle inequality theorem. So the triangle inequality theorem states that the sum of the length of any 2 sides of a triangle are greater than the third. This shortens down to sum of lengths of 2 sides of triangle must be greater than the third side. So in other words, we would create 3 separate statements. We can say that any combination of 2 sides is greater than the third side. So here's all of our possible combinations. All right, so let's take a look at this theorem in action by looking at example 5. A triangle has one side length 14, another side length of 9. Describe the possible lengths of the third side. So we would have to do 2 setups. We'd have to look at the third side as if it were the shortest. In other words, find the smallest possible x value. And then we'd also need to look at treating the third side as the longest, or in other words, the largest value of x possible. So when we do that, we would set up a picture similar to these, and we would realize that we would treat the 14, the bigger value that we're given, as if it were the longest side, which means we need to figure out the shortest possible value, call it x, and then the other number that we're given, which is 9, would be our other side length. So that means we need to add the 2 smaller numbers, the x and the 9, and treat it to be greater than that longest side. And then for finding the largest possible value, we would treat the 9 and the 14 that we were given as the shorter lengths, and x is our longest, which means you add the 2 smaller lengths, and they must be greater than the long one. So when we solve both of these inequalities, we get a value of x greater than 5, and we get a value of x less than 23 if you read this backwards. So we combine it to have a compound inequality, which states that the 5, which is your lowest possible value for x of the third missing side, is less than x less than 23, 23 being the longest possible value you could have for x if you're given 2 lengths of 9 and 14. So the length of the third side must be greater than 5 and less than 23. So in other words, mainly what you're doing is you're figuring out each value. One value is you subtract the sides that you're given. The other value, you add the sides that you're given. All right, so you try these on your own. Pause the video, take a moment and try these, and then unpause the video to see if you got them right. Okay, check your answers, see how you did. Did you get that the lengths of the third side for number 4 must be greater than 8 and less than 32? And for number 5, all possible combinations work out to be yeses, so therefore the sum of any 2 side lengths of a triangle is greater than the third. So combinations of 4, 9, and 10 will form a triangle. And then for numbers 6 and 7, neither one of these will result in forming a triangle. For number 6, the sum of 8 plus 9 equals 17 is not greater than 18. And then for the sum of 5 plus 7 equal to 12 is not greater than 12. And that's all for today. So bring any clarifying questions to class tomorrow.